All right, here we are for AP Physics Potential Energy. Going to work through problem 1 here. Problem 1 says, I have a 10 kilogram block. We're going to release it from rest at point A on a frictionless track, except it's rough right here between B and C, between these positions, that 6 meter long stretch. So it's going to travel along faster, 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 constant speed till it hits that rough patch. And it's going to actually go past that. It's going to hit a spring here. They give you a spring constant and compress that spring 0.3 meters before it comes to rest momentarily. Of course, then we get like launched back again. It would be an exciting problem to see how high it would get when it goes back. But a little repetitive. So anyway, we're not going to do that. We just want to find the coefficient of friction between B and C, knowing it's going to crush this spring 0.3 meters when it gets there. Okay, so we are doing an energy calculation here, and we're going to go from here when we release it, because we kind of know everything there is to know about it when it's there, until it's fully crushed here. Okay, we're going to kind of analyze that motion from A to, probably should give it a name, like call the position where it's crushed here, call that D when it's crushed all the way down, that 0.3 meters. So we're going to go from A to D. So that is kind of my plan, and I'll get a big energy equation. And one of the things, remember, we'll look at every force acting on it, right? Work terms for every force acting on our system between there and there. One of those work terms will be from this friction force there. And in that work term, we'll have the force of friction. And in the force of friction equation, we'll have mu times the normal force. So we'll be able to solve for that mu, that coefficient of friction, in that way. That is my big overall master plan for this problem. Okay. I don't know that you necessarily should spot that immediately when you see this. When you see a problem like this immediately, I'd like to think that if you see height changes and you see a spring getting crushed or stretched, you should right away start thinking energy is a good way to go. And now I know, of course, we're in the energy unit now, but I'm just saying in the future, when you see a problem like this, springs usually are an indication that energy would be a good thing to look at, and height changes, probably using gravitational potential energy. And so you should start thinking that way when you see a problem laid out like that. Okay, so here we go. So that is my plan. So I'm going to work on a separate paper, so I got plenty of space. Okay, I am going to draw the sketch over again. Sorry, you wouldn't have to do this probably on an AP exam. Hopefully they would have the whole sketch there for you, just write on your sketch. But be careful. It used to be the case that you would get a green packet that had all the problems, but there was a separate packet where you wrote your answers, like a pink packet. And anything you wrote on the green packet wouldn't get scored, only stuff you wrote in the answer form. So you want to be careful about that. Make sure the stuff you wanted to score is there. Okay, so here we go. Position A. Why am I doing this in pencil? All right, because I'm doing this for you. I want to make sure I'm writing boldly so you can see what the heck is going on. Sorry about that. Yeah, this is my starting position is A. B is where it enters that rough stretch. C is where it exits the rough stretch. I'm going to introduce a spot here, D, which is crushed down by 0.3 meters. Okay, I'm going to do my analysis. Let's see, what else do we know? We know they tell us our height change here is 3 meters. Okay, they tell us that this rough stretch here is 6 meters. Okay, and they tell us that the spring constant is 2,250 newtons per meter. Oh yeah, and we know that the mass of the block is 10 kilograms. All right, there we go. Okay, so I am setting up, anytime you do an energy calculation, you always have a starting and ending position. So we are going from A to this position D, where it is stopped again, right? Where it's about to get launched back again by that crushed spring. So that is the plan. So here we go. Big energy balance, okay? The big formula. You say, I know the big energy formula. It is the work energy theorem. Sigma W is delta K, all right? All right, this is for my system being just the block, okay? And going from A to D. Okay, so this equation is specifically set up for that. Here we go. I'm going to put in a work term for every force. So I'm thinking about all the forces that are acting on the block as it goes between A and D. And you say, well, there is a normal force from this surface. There is a gravitational force pulling down on it. There is a friction force when it hits that rough patch, and there's a force from the spring. Okay, those are the four forces they're acting on as it moves from here to here. If you need to sketch some force diagrams to verify that those are the only forces acting, be my guest. Delta K, that's going to be the K at ending minus starting. You know what I'm saying? K at D minus K at A. Now, real quick, running through this, some of these terms may very well drop out. You say, yeah, hey, I know that we are starting here at A. The V at A is 0. And so the starting kinetic energy would be 0. Because that drops out because the V at A is 0. And I know that the end, when I get to D, it's brought to rest by spring and then it will get launched back. I know the V at D is 0, so the final kinetic energy will be 0 because the V at D is 0. So that's good news. That's 2 terms gone. The normal force is going to act in this problem perpendicular to the motion the whole time. So that's going to drop out because normal is perpendicular to the motion. All right, which just leaves me with these 3 terms. This is looking better already, only 3 terms. Now, work done by gravity along a curved path, and they don't tell you like the radius of curvature or anything like that. We're going to use potential energy for sure. So that means I'm going to alter my system. It'll be the block and the Earth. So now the gravitational force won't be an outside force on the system. I'm going to be rearranging that system, though, changing the amount of potential energy it can do, that Earth block system. So this is going to go away because gravity is not an outside force, but instead over here, I'm going to have a delta UG. I'll have a UG final minus UG. So our final at D minus the UG at A, right? Final minus initial. Friction, that is going to be an outside force doing work along here. So I'm going to leave that term alone. I can't write a potential energy function for friction. It's a non-conservative force. I'm not allowed to write a potential energy function for it. The spring, though, a Hooke's law spring, that's going to be a conservative force. I can write a potential energy function for that, and I will. Okay, so I'm going to expand my system to include the spring. You pretty much almost always would rather do a potential energy function rather than a work function. Okay, almost always. So this would be the U spring at D minus the U spring when I started, right? Now, these terms. With potential energy functions, we got to set where the potential energy is 0. Where would you like to call height 0? Me too. Let's call this height here 0. Well, that's the height at B and at C and at D is 0. So if the height at D is 0, the potential energy at D is 0, that drops out, okay, because the height at D is 0. Potential energy of the spring, we know that while the block is here, all through here, there's no energy stored up in the spring yet. The spring's not crushed yet. So when the block is at A, there is no energy in that spring yet. Okay, the spring is at x equals 0 at that point. So I'm really just looking at this final. So I still just have 3 terms, 1, 2, 3. That's not bad at all. Rewriting my energy equation showing only the non-zero terms, it would look like this. The work done by friction is going to equal minus the gravitational potential at A plus the gravitational potential energy at D. I mean, the spring potential, it's an S. Sorry, that's an S, spring. Okay, so look what's happening. I'm gaining energy in the spring. I'm losing the gravitational potential energy I started with. But there's also going to be some energy entering or leaving the system because of friction. In this case, it's leaving the system, right? That friction force, this is going to end up being a negative term when I do the calculation for the work done by friction in here. So I'm losing gravitational potential energy, and my system's losing some more energy, leaving the system, actually. But what's left over is turning into that energy in the spring. Okay, so that's the big picture, which is part of why I like that line. It lets you see with the big picture what's happening energy-wise. All right. That's a subscript S. That's really annoying. Moving onward. Hey, let's go ahead and put in our formulas for work, for gravitational potential energy, and for spring energy, that elastic energy. So work, I know that's the integral of F dot dx. All right. For gravitational potential energy, that's going to be minus mg, the height at A. And elastic potential energy, 1/2 k, the crush distance at d squared. Okay, these are just the formulas we have for those energy types. Now the work, when I do this, you say, hey, I know that that angle between the friction force and the motion, we're going to be moving to the right, and friction is going to be going to the left against the motion. That's going to be 180 degrees off. It's going to be a cosine of 180 from that dot product, which is just a -1. And it's going to be a constant while we're sliding along. While we're sliding along, is that kinetic friction going to be changing? No, it's a constant value. So you're like, oh my gosh, constant force can come out of the integral, constant angle here, so it's going to be constant cosine, -1 pops out. Integral dx, that's just the delta x. Hey, this just turns into minus friction delta x. All right, it really turns into that basic work F dot delta x that we had from last year, because these are constant force, constant angle. All right, on the other side, all right, actually let's continue with this a little bit more. The force of friction, we can write an equation for it. We are trying to find the coefficient of friction. That is what we are trying to find in this region. Hey, what is that mu? All right, and so we're going to substitute in the friction formula here for kinetic friction. That is mu times the normal force. Okay, so at last we have the variable we're trying to find in our equation. That's a very good thing. But I need to find that normal force there. I really should have done a force diagram here at this point. Let's go ahead and draw that in. I know that you kind of, at this point, can you kind of picture it in your head already, I think you can. I think you can. While the block is sliding through this part, wouldn't you agree that, I'm just going to squeeze it over here. Look at that. Look at that. Wouldn't you agree that as it's sliding along that rough patch, right, that I would have a gravitational force, I would have a normal force from the surface, and I'd have that friction force opposing the slide, and that's it. There's nothing. The only thing touching the block is the surface. That's just the normal and the friction from it. That's it. And so it'd be like, you know, the normal force would be equal to mg here. No biggie. Okay, that delta x, we know what that is. That's just the stretch here, that's 6 meters while it's going through the rough patch. On the other side, we've got, let's see here, mg, height at A. You're like, we know all these values. We know the mass, 10 kilograms. We know g. We know the height at A was 3 meters. We know the spring constant. We know the distance it crushed the spring was 0.3 meters. We know all these values. Hey, we know everything here except mu now. We do. I'm just going to bring this down. I'm just going to bring these terms down. I'm not going to bother writing it out in every line. How would I do that? This all just tracks down. Okay, I know all these values. I can solve for mu. I'm just going to stick my values in right here and call it a day here once we get this math. This is going to be mu, yeah, sure, why not, times 10 times 9.8 times, it slides through 6 meters, minus 10 kilograms times 9.8 times a height of 3 meters plus 1/2 spring constant of 2,250 times a crush distance of 0.3 meters squared. There we go. That's the math I'm going to solve with my calculator. Here, let's do it. Let's do it. Doomby doomby doomby. 0.5 times 2,250 times 0.3 squared minus 10 times 9.8 times, did I just do that wrong? Of course I did. 9.8 times 3. All right. Okay. Now that sign is going to flip when I multiply through by -1 and divide by 98 times 6. I get a mu of 0.3278. You say there's no units on a mu. You're like, okay, that's more digits than I really have precision here. I think they gave me 3 sig figs, so I really ought to round this to the 3rd digit. I really ought to report this mu as a 0.328. I know, as soon as I start talking about sig figs, people are like, Mr. C, do we have to worry about sig figs on the AP exam? Not so much. Just don't over round. You know, don't round it down too much. 0.3, probably not enough. Okay. Okay, there we go. That's my answer.